Hi, this is Mrs. Evans, and today I'm going to do some examples of antiderivatives of trig functions, and we're going to use identities when we need to. So today is going to test not only your calculus and how to take antiderivatives, but it's also going to test what you know about trig. So go ahead and get out your notebook and see if you can find some of your old trig identities and formulas and properties, because those might help you. In your notes, I need you to get these 4 problems written down. So go ahead and pause this video and write these 4 antiderivative problems down, and we'll go ahead and work these. Our first antiderivative problem is the antiderivative of tangent squared y plus 1. If you are taking the antiderivative of a trig function, it is very helpful to think like you would with Jeopardy. You want to think about that this is the answer. So what was the question? In other words, you want to be able to say to yourself, I have a trig function, and when I take the derivative of it, I get this as my answer. So it's really best if you know all of your trig derivatives. So over here on the right, I have all 6 main trig derivatives. If this is not one of the answers, then I have to do some manipulating. Now I could manipulate by splitting this into 2 separate functions and doing the antiderivative of tangent squared y and the antiderivative of 1. But when I look over here, I don't see the antiderivative of tangent squared in my answers. So I don't think that's going to help me either. So what I'm going to need to do is I'm going to need to think back to some of my trig identities. So when I'm thinking about my trig identities, the first one that comes to mind for me when I'm dealing with a function that's a trig function squared is my Pythagorean identities. Sine squared plus cosine squared equals 1 is the one you use mainly. But right now, what I can see is I have a 1 plus tangent squared equals secant squared. So what that means to me is that I can take this function right here and I can change it into secant squared. So what I'm going to do with this problem is I'm actually going to rewrite tangent squared plus 1 into secant squared. And then I'm going to think to myself, what trig function do I take the derivative of that gives me secant squared as an answer? And you'll notice over here, tangent of x is equal to secant squared. So the antiderivative of secant squared y dy is tangent y plus c, and that's my answer. So one of the secrets to being really good at taking antiderivatives is that you always check your answer. You can check your answer by taking the derivative of your answer and seeing if it gives you the original function. This is especially true with trig antiderivatives. It's very helpful. So here's our last question and our answer. So what we're going to do is we're going to check it real quick. In order to check it, we're going to take the derivative of the answer, the derivative of tangent y plus c. Well, I know the derivative of tangent is secant squared, and the derivative of a constant just goes away. So I have secant squared y. Then what I also know is that when I use a Pythagorean identity, secant squared y is tangent squared y plus 1. So this was my original problem, and I know I'm correct. So my next problem is the antiderivative of 4x minus cosecant squared x dx. And I can tell right now by looking at this that this isn't going to be the answer to just a normal trig. So I'm going to look at my trig derivatives. And what I do notice is that I do have right here this part of my integrand. So instead of trying to manipulate it using an identity, I can actually just split this one. I can split 4x minus cosecant squared x dx into the antiderivative of 4x dx minus the antiderivative of cosecant squared x dx. Then I can take the antiderivative just normal of 4x by adding 1 to the exponent, which gives me x squared, and then I divide by that 2. 4 divided by 2 is 2. That's what gives me 2x squared. And cosecant squared, negative cosecant squared in particular, is the answer to the derivative of cotangent x. So I get cotangent x, and I can't forget my plus c. Remember, when you do antiderivatives, you always want to do a plus c. So remember what I told you? You want to check your answers. So the original question was the antiderivative of 4x minus cosecant squared x dx, and my answer was 2x squared plus cotangent x plus c. In order to check, I start with my answer, 2x squared plus cotangent x plus c, and I take the derivative. The derivative of 2x squared is 4x. The derivative of cotangent is negative cosecant squared, and the derivative of any constant is 0. So my answer is correct. So this is actually a really good problem. In this problem, what I notice is that I have a quotient. And what I need to remember is that I cannot take the antiderivative of the numerator and take the antiderivative of the denominator. That's not allowed. Just like quotient rule must be used with derivatives, and you can't just take the derivative of the numerator and the derivative of the denominator when you do quotients. But there is no reverse of the quotient rule with antiderivatives, so we're going to have to do some manipulating. So look at this and see if you can think of where we can manipulate this integrand. So again, when I have something with a squared in it, I start automatically thinking about a Pythagorean identity. So in this case, I have 3 Pythagorean identities, and that denominator doesn't look identical to any of those. However, this first one, sine squared plus cosine squared equals 1, can be manipulated, and I can move the cosine squared to the other side, and I'll get 1 minus cosine squared is equal to sine squared. So let's see what that gets me. So since we know we can change the bottom into sine squared x, we have another quotient, the antiderivative of cosine x over sine squared x. Well, remember before when we were talking about the quotient, I really couldn't do too much with it, so I had to think about how to change that. And anytime I'm trying to change something with trig and quotients, I think of 2 different things. One thing I think about is my reciprocal identities. Notice I have a sign in the bottom. So over here on my reciprocal identities, I'm looking for anything that has a sign in the bottom. And what I notice is that I have cosecant x is 1 over sine of x, but I don't have a sine squared. So I have to think a little bit more about what I might do. So what I'm actually going to think about is, what about my tangent and cotangent identities? And I'm looking again for a sign in the bottom. Well, right here, I have a sign in the denominator. But again, just like before, I have just a regular sign and not a sine squared. But if you look at this one and this one together, imagine multiplying 1 over sine x times cosine x over sine x. So what I'm going to do is split it into 2 identities. 1 over sine x times cosine over sine x. 1 times cosine is cosine. Sine times sine is sine squared. 1 over sine of x, what I had remembered from my reciprocal identities, is cosecant x, and cosine over sine x from my tangent and cotangent identities is cotangent x. So what that gives me is cosecant cotangent. And if you'll remember from your derivatives, the derivative of cosecant is negative cosecant cotangent. Well, I have positive cosecant cotangent. So in order to fix that, I just need to put a negative in front of my answer, because the negative of this derivative will end up giving me a positive cosecant cotangent. And I can't forget my plus c. So let's check our answer. Cosecant x over 1 minus cosecant squared x was my question. My answer was negative cosecant, so we're going to start with the derivative. The derivative of negative cosecant is positive cosecant cotangent. I can switch cosecant into 1 over sine, cotangent into cosine over sine, and when I multiply those together, I get my original integrand. So here's our last problem. Sine of x over 1 plus sine squared x. What I'd like for you to do is to pause this video and try this one on your own, because it's better if you try it before I show it to you. So did you notice that this denominator is a Pythagorean identity? If I move sine squared over to the other side, I have 1 minus sine squared. So I can replace the denominator with cosine squared. So my new denominator, or excuse me, my new integrand is sine over cosine squared. Well, what we also need to remember is that we can split the integrand into two separate fractions. You can think about it as in 1 over cosine x times sine over cosine x, because if I multiply those together, that gives me my integrand. And what's the point of that? Well, the point of that is the fact that it then becomes 1 over cosine is secant x, sine over cosine is tangent. And if you remember, that is actually the answer to one of your trig derivatives. The derivative of secant x is secant tangent. Don't forget your plus c. And here's your quick check. The derivative of secant is secant tangent. The derivative of c is 0. Secant can be converted into a reciprocal identity of 1 over cosine, and tangent can be switched into sine over cosine. That together makes sine over 1 plus sine squared, which was my original integrand, so I know I'm correct. Thanks for watching, and we'll see you next time.